Hello everyone, welcome back to Sulekha physics classes. Hope you all are doing well. Today I am going to start next part of this chapter, Human Eye and Colorful World. In this part I will cover atmospheric refraction and different phenomena based on atmospheric refraction, like twinkling of stars, why stars appears higher than they actually are, advanced sunrise and delayed sunset. All these are based on atmospheric refraction. And after that I will discuss scattering of light and different phenomena based on scattering of light, like why blue color is a blue color of the sky, then why sun appears reddish at sunrise and sunset, why cloud appears white. We'll discuss all these things one by one. So let us start today's topic with atmospheric refraction. Now, atmospheric refraction. What is atmospheric refraction? Refraction, you know, bending of light when it travels from one medium to another medium. This is called refraction. Then what is atmospheric refraction? Atmospheric refraction means bending of light when it travels through different layers of the atmosphere. This is called atmospheric refraction. Here refraction takes place due to different layers of the atmosphere. When light enters through different layers of the atmosphere, refraction takes place. So the refraction of light caused by Earth's atmosphere is called atmospheric refraction. But why this atmospheric refraction takes place? Why bending of light takes place when it travels through the atmosphere? You know, atmosphere is not uniform throughout. Like Earth's atmosphere is not uniform throughout. Its density changes as you move up or down through the different layers of the atmosphere. And due to change in density in different layers of the atmosphere, what happened? Its refractive index also changes. Top layer of the atmosphere acts as rare medium and bottom layer of the atmosphere acts as denser medium. It means when you move down, right, its refractive index increases, so lower part of the atmosphere acts as a denser medium and upper part of the atmosphere acts as rare medium. Now it's easily you can observe that when light ray enters, suppose this is the position of object. So you know this one is vacuum. Vacuum is free space. In free space, light travels with the speed of light. There is no change in medium. So light from this object travels in this way, right now. But when it reaches the Earth's atmosphere, these are different layers of Earth's atmosphere. This one is Earth. Above this Earth, atmosphere is there. So when light ray reaches at this point, now here if you draw one normal, so instead of going like this straight line path, its path changes due to change in density or refractive index. When light enters from rare to denser medium, it bends towards the normal. So instead of going like this way, it bends like this direction. Again at this point you draw one normal. Instead of going like this one, again it changes their path. So in this way, at different layers of the atmosphere, it changes their path, and when it reaches, suppose observer is at this point on the Earth. When light reaches to the observer, it appears to come from this position, right now, and this one is apparent position of the object, apparent position, and this one is actual position, right? So actually the object is at this point, but when it enters through the Earth's atmosphere, its path changes, it takes curved path, like, and when it reaches to the observer, it appears to come, light appears to come from this point. It means the object appears at this position to this observer. It means observer is not able to see its actual position. Observer observes its apparent position. So due to atmospheric refraction, position of the object changes, right? Also, the temperature of different layers of the atmosphere also changes with time. So due to change in temperature with time, this apparent position is also not fixed. It also changes, right now. So due to this, atmospheric refraction takes place and apparent position also changes with time. This is about atmospheric refraction. So you write these 2 points. First you write the definition. The refraction of light by the Earth's atmosphere is called atmospheric refraction. And why this atmospheric refraction takes place? Because the Earth's atmosphere is not uniform throughout. Its density goes on changing as you move up or down. The upper layer is rare as compared to the lower layers of Earth's atmosphere, and due to this difference in density, when light ray passes through Earth's atmosphere, they undergo refraction, and due to this atmospheric refraction, you are not able to observe the actual position of the object in the sky. You are able to observe the apparent position, and apparent position also changes with time due to change in temperature of different layers of the atmosphere with time. This is about atmospheric refraction. Now after this, I will discuss 2 important phenomena of this atmospheric refraction. First, the object appears higher than the actually they are, and also second, the twinkling of stars, and next phenomena of this atmospheric refraction is advanced sunrise and delayed sunset. So I will discuss all these phenomena one by one. First, to take a screenshot of this one fast. Now some phenomena based on atmospheric refraction. First one is the stars seem higher than they actually are, and it is due to atmospheric refraction. We already discussed before this one now what is atmospheric refraction, and you are able to observe the apparent position of the object in the sky instead of actual position. How it happens? Suppose this is the actual position of a star, and you know light ray coming from these stars. There are different light rays coming from this star, right? Now these rays, when it enters inside the Earth's atmosphere, from here different layers of the Earth's atmosphere starts, right? And this one is surface of the Earth, right? So when light from this star is coming and enters inside the Earth's atmosphere, what happens? What happens? You know, refractive index is increasing in downward direction. So it means upper layer acts as a rare medium and lower layer acts as a denser medium. So when light rays from the star enters inside the Earth's atmosphere, instead of going straight, it bends its path towards the normal, and at different layers its bending is different. It suffers multiple refraction inside the Earth's atmosphere, and instead of moving straight and reaching at this point, it reaches to this point on the Earth. And suppose observer is at this point, so when the observer observes this position of a star, the light coming, it appears that when you extend in the backward direction, it appears to come from this position, and observer is able to observe this position. This is not actual position, this is actually apparent position, and this position is only due to atmospheric refraction, atmospheric bending, right now. So when light enters from a star inside the Earth's atmosphere, it undergoes multiple refraction, bend towards the normal each time due to atmospheric refraction. At every point there it suffers multiple refraction. Then on producing final refracted ray, when the observer is near the horizon, when final refracted rays is produced in backward direction, then the apparent position is always slightly higher than its actual position. Right now you are not able to observe the actual position of the star, and you are when you observe the apparent position of it is always actually higher than the actual position of the star, and these are all due to this atmospheric refraction, right now. So after this, again this apparent position is also not constant, it changes with time, and that effect is called twinkling of stars. So please take a screenshot of this one first, then we will discuss second phenomena, twinkling of stars. Now second phenomena based on atmospheric refraction is twinkling of stars. What does it mean? You know, stars always appear at the apparent position, not at the actual position. We already discussed, it's always appear at the higher than the actual position, right? Suppose this is a position of a star, and due to atmospheric refraction, observer observes this apparent position of the star. Okay, you know. But this apparent position of the star also changes with time. It is not stationary. It continuously changes. Why? Due to physical conditions of this atmosphere. Temperature varies with time. So due to change in physical conditions of the atmosphere, the apparent position of the star also changes. Sometimes star appears at this point, sometimes it appears at this point, sometimes at this point, sometimes at this point. So the apparent position of the star changes with time, and the amount of light entering the observer's eye also changes. It flickers. It is not stationary. It changes continuously, and that is called twinkling of stars. Is it okay? So you can write distant stars. First you write distant stars acts like a point source of light. This star is at very far from the Earth's atmosphere, Earth's surface. So this star acts like a point source of light. As the beam of star enters the Earth's atmosphere, when it enters the Earth's atmosphere, what happens? It changes their path when it reaches the observer's eye, and it suffers multiple refraction. It changes their path at every point on the Earth's atmosphere. The apparent position of stars keeps on changing. It is not stationary. First apparent position is this point. Second position, star appears at this point. This apparent position is not stationary. It changes continuously because physical conditions of Earth's atmosphere is not stationary, like temperature, pressure. Okay. Hence, the amount of light entering to the observer's eyes fluctuates. Fluctuates means sometimes it appears bright, and sometimes it appears dim. It means the amount of light entering the observer's eye flickers, and that effect is called twinkling of stars. Hope it's clear to all of you. What is twinkling of stars? You know, a star always appears at a position higher than the actually there. That is called apparent position, and that apparent position of the star is also not stationary due to physical conditions of the Earth's atmosphere is not stationary. It is not stationary. It changes with time. Hence, amount of light entering eye fluctuates. Fluctuates means flickers. Flickers means sometimes it appears brighter and sometimes it appears dimmer. Hence, this effect is called twinkling of stars. But only stars twinkle. Planets do not twinkle. Why? Why planets do not twinkle? The reason is simple, and it is also important. May ask in 1 or 2 marks question. Why planets do not twinkle, only stars twinkle? Actually, planet is much closer to the Earth's surface, and it is much bigger in size than the star. You can say that planet can be considered as a collection of large number of point-sized objects. So, different parts of these planets produce brighter or dimmer effect in such a way that the net effect is zero, and observer is not able to observe the twinkling effect of the planets. That's why planets do not twinkle. Reason is simple, because planet size is very much larger than the star, and different parts of these planets produce the effect bright and dimmer in such a way that the net effect is zero. That's why planets do not twinkle. Hope it's clear to all of you. Please take a screenshot of this one. Then we move to the next phenomena. Now, next phenomena of atmospheric refraction is advanced sunrise and delayed sunset. What does it mean? Advanced sunrise means the sun appears to rise above horizon 2 minutes before it actually is above the horizon. Sun is actually below the horizon, but it appears to rise 2 minutes before above the horizon, right? This is called advanced sunset, and it is also due to atmospheric refraction. I will explain it. Okay, what is delayed sunset? The sun can be seen about 2 minutes after the actual sunset. Actually, the sun is at this position during sunset, but it appears to be at here 2 minutes after the actual sunset. This is called delayed sunset. Why this happen? Why there is advanced sunrise and delayed sunset? There is a 2 to 4 minutes difference between actual sunset and apparent sunset, right? Similarly, actual sunrise and apparent sunrise, there is 2 to 4 minutes difference. Why this happen? Okay, during sunrise, the sun is near the horizon, and when the light from the sun enters the Earth's atmosphere, what happened? Inside the Earth's atmosphere, density increases near the surface of the Earth. It becomes more dense. It means density is high. So, light ray from the sun enters inside the Earth's atmosphere. It bends towards the normal due to change in density from rare to denser medium, and appears to the observer that the sun light ray is coming from this position. So this apparent position is seen by the observer, right? Actually the sun is at this position, but the observer sees 2 minutes before the actual position. Observer seen this apparent position of the sun. That's why the sun appears to rise above 2 minutes before it actually is above the horizon. In the same way, during sunset, actual position of the sun is this one. But due to atmospheric refraction, the observer sees this apparent position of the sun. So it means the sun can be seen 2 minutes after the actual sunset. This is called delayed sunset, right? And this is also due to atmospheric refraction. So this is about advanced sunrise and delayed sunset, and both are due to atmospheric refraction. Hope it's clear to all of you. Please take a screenshot of this one. Important topic of this chapter is scattering of light. What is scattering? And students generally confused between scattering and dispersion of light. There is a large difference between these two. Dispersion is actually splitting of white light into its constituent colors, and reverse is true. In Newton's experiment, it is proved that when all these constituent colors again recombines to form white color. But in case of this scattering of light, reverse is not true, and also it is spreading of light in all possible directions by some particles present in the atmosphere, like dust particles, free water molecules. Okay, so this scattering of light is spreading of light in all directions by the dust particles, free water molecules present in the atmosphere. Actually, what happens when light rays collides with these dust particles or water molecules absorbs that light and again re-emits this light energy. So it is process of first absorption and then re-emission of light energy. This is scattering of light, and scattering takes place in all possible directions in an irregular manner, right now. So is it clear? It is a process of absorption and then re-emission of light. Suppose this is any particle, a scatterer, okay, and light collides with this scatterer, then this is incident light, okay, this is incident light. Then after colliding with this particle or a scatterer, first it absorbs this incident light energy, then again re-emit this light energy in all possible directions. It spreads light energy in all possible directions. This is a scattering of light, and this scattering also depends on this size of the scatterer. If the size of the scatterer is smaller than wavelength of light or near about wavelength of light, then only this scattering is possible. But okay, this is possible only if this size of the scatterer is smaller or equal to the wavelength of light incident on this scatterer. But if size of a scatterer is larger than the wavelength of light, then what happens? Scattering is not valid. If the size of the particle is larger than the wavelength of light used, then in this case scattering is not possible. In this case, what happens? Scattering is there, but it scatters all wavelength equally. It means scattered light intensity is equally, it again appears white. So scattering is not possible when wavelength of light used and size of the particle is greater than the wavelength of light used. Again, according to Rayleigh scattering, okay, formula is this way: intensity is inversely proportional to lambda to the power 4, fourth power of wavelength. It means smaller wavelength, it has greater intensity. Larger wavelength, it has smaller intensity. Intensity is related to scattering, right? Scattering is inversely proportional to wavelength of light. Scattering is related to intensity. Greater intensity means greater scattering. Smaller intensity means smaller scattering. So intensity is inversely proportional to fourth power wavelength. then also scattering is inversely proportional to wavelength of light used, right? And you know wavelength increasing in this order from violet to red. So violet has minimum wavelength, red has maximum wavelength. It has lambda maximum, red color, and here violet has lambda minimum. If violet has minimum wavelength, it means scattering for violet color is most. Violet color scatters most than red color. So this one is important. Violet colors scatter most. So there are different phenomena based on this scattering of light, like blue color of the sky, okay, red color appear at the sunset or sunrise. All this happens due to this scattering of light only. There is another thing, if a scattering of light takes place by collided particles. Here dust particles, free water particles present in the atmosphere. But if a scattering takes place by collider particles, then that effect is called Tyndall effect. It means it makes path of light visible. Suppose there are two beakers, okay? There are two beakers. In one beaker water is present. In another beaker you add some milk also in this water. So when light ray passes through this beaker first in which water is kept, what happens? Here in water there is no small particles. All particles are mixed properly, uniform, homogeneous mixture is there. It means no scattering is possible in this case because there are no dust particles present in this water in A beaker, right? And suppose this one is B beaker. Here particles are present. That particles are called, milk, it is colloidal particles. And if colloidal particles is present, then in this case if light ray passes through this beaker, you are able to see the path of the light. It makes the path visible, and this effect is called Tyndall effect. Here water is present in this beaker, here milk is added in this beaker. So in first beaker no scattering takes place because it is homogeneous mixture, such as the particle is very, very small. But in second beaker milk is present and milk is a colloidal particle, size of the particle is larger. So here scattering is possible and it makes the path visible. This effect is called Tyndall effect. Okay, so after this I will discuss some phenomena based on scattering of light. First is blue color of a sky, after that red color of sun at sunrise or sunset. Please take a screenshot of this one. Okay, now some phenomena based on scattering of light. First one is blue color of sky during daytime. Why sky appears blue during daytime? It is also due to scattering of light. How this sky appears blue? Suppose this one is Earth's atmosphere, okay, and light is coming from this sun during daytime, okay. Light is coming and in vacuum, this is free space, it traverses straight line, okay. But these are different layers of Earth's atmosphere, right? These are different layers of Earth's atmosphere. And in Earth's atmosphere, there are large number of air molecules, right now. So when the sunlight enters into this Earth atmosphere, what happens? These sunlight is scattered by the air molecules and scattered in all possible directions. White light consists of all 7 colors, that is Vibgyor, violet, indigo, blue, green, yellow, orange, red, and wavelength increases in this order. It means these 3 have shorter wavelength and this side yellow, orange, red has larger wavelength, and scattering is inversely proportional to wavelength of light. It means wavelength of this violet color is less than wavelength of red color. So intensity of violet, indigo and blue color is more than that red light, right? Intensity of scattered blue light is more than red light. So that's why in the sky blue color is scattered in all possible direction. Right now blue color is scattered in all possible directions. When the observer observes the scattered light in the sky, it appears blue. That's why sky appears blue during daytime. So only the scattered blue light enters our ears and sky appears blue. So these are the reason why sky appears blue. It is due to scattering of light. When light from sun traveling through this Earth's atmosphere, it gets scattered by different number of particles near the Earth's atmosphere, so it gets scattered. And you know, violet color has shorter wavelength than red color, and scattering is inversely proportional to wavelength, na? Scattering is inversely proportional to fourth power of wavelength. Shorter the wavelength, more is the scattering. So violet, indigo and blue color has shorter wavelength. So intensity of violet, indigo and blue color is more than red color, right? That's why the scattered blue light enters our ear. Suppose observer is on the surface of Earth. Okay, and only the scattered blue color reaches our eyes and sky appears blue. This is the reason. Also, one more thing, if this Earth had no atmosphere, if the atmosphere is absent, then what happens? There is no scattering of light takes place. Scattering is only possible if atmosphere is present. Inside the atmosphere, there are large number of molecules whose size is smaller than that of wavelength of light. That's why scattering is possible. If there is no atmosphere, no scattering is possible, and hence the sky appears black. So when 1 marks question, it may ask, what happens if Earth had no atmosphere? In that case, sky appears black because there is no scattering of sunlight if atmosphere is not present. So this is the reason why sky appears blue color, and if there is no atmosphere, then the sky appears black color, right? Okay, please take a screenshot of this one. Then we move to the next topic. Now, next phenomena based on scattering of light is sun appears reddish at the time of sunset and sunrise. During sunrise and sunset, the color of the sun is red. Why? You know, during sunset or sunrise, the sun is near the horizon, right? And in that case, the sun has to travel larger distance through the Earth's atmosphere. So what happened? Blue color, violet color has minimum wavelength, so it scatters away, and only red color, which has larger wavelength, it reaches our ear. That's why the sun appears reddish during sunrise or sunset. So you have to write reasons like this one. During sunset and sunrise, sun is near horizon, right? So sun has to travel longer distance in the atmosphere because sun is near the horizon and it has to travel larger distance near the atmosphere, right? And hence most of the blue color is scattered away because blue color has shorter wavelength. Only red color, which has largest wavelength, is scattered least and enters our eyes. That's why sun appears reddish in color. Is it clear? So you have to write these points during sunset and sunrise. Sun is at which position, then which color is scattered most and which color reaches our ear. Only red color reaches our ear because red color has largest wavelength. One more thing, during noon or afternoon, what happens? Sun is nearly overhead. So when sun is nearly overhead during afternoon, then the sun travels much shorter distance in atmosphere. Hence scattering is less. When the sunlight travels shorter distance, so scattering is very small amount and the sun looks white during noon time. So one more thing, this is also important why during afternoon sun is appears white in color, because sun is near overhead and the sun travels much shorter distance in the atmosphere, hence scattering is less, so the sun looks white. Next, why danger signals are red in color? You know, all the danger signals are red in color. Why? Because the red color has larger wavelength, so it has to travel larger distance, so we can see red color from the very far point. That's why danger signals are always red in color, because you can write it this way: red color has largest wavelength, hence scattered less, therefore only red color can be seen from the farthest distance and hence danger signals are red. It reaches our eyes. Okay, now one more last phenomena based on scattering of light is white color of clouds. Why cloud appears white in color? Because clouds are at much lower height. And what happens when the clouds are at much lower height? Cloud contains dust particles and water molecules which are bigger in size than the wavelength of light. And if size of the dust particles in clouds and water molecules is bigger, the size of a scatterer is bigger than wavelength of light, and we already discussed is size of a scatterer is larger than the wavelength of light incident. In that case, Rayleigh scattering is not valid. It means it scatters all colors of incident light in same amount. Right now, it scatters all colors of incident white light with same amount. It means intensity of all colors of the scattered light is same, and hence cloud appears white. So this is the reason why cloud appears white, because clouds are at much lower height and the dust particles and water molecules in the clouds are very bigger in size than the wavelength of light used, and here Rayleigh scattering is not valid. So it scatters all colors of incident light with the same amount, hence intensity of all scattered colors of all the colors of the light is same, and hence cloud appears white. So these are different phenomena based on scattering of light. Hope it's clear to all of you. Please take a screenshot of this one. With this, I am going to end the class. Hope you understood each and every point of today's session, right? So up to then, students, please keep revising and stay tuned with this channel. Thank you.